let's calculate the magnetic field associated with a ring of current. So let's suppose we have a ring of current, and the current is going this way. Now, in particular, let's calculate the magnetic field just along this axis, the z-axis, and let's pick a point up here, which we'll write as 0, 0, z. And so this distance is z. And I want to calculate the magnetic field at that point. Now, the way we're going to do this is, again, we're going to use the Biot-Savart law. So the Biot-Savart law is the magnetic field at the point z along this axis, I'm skipping the x and y components, is the integral over the ring of a constant mu naught over 4 pi times our source, infinitesimal current source element, cross a unit vector r, which is going from the source element to the field point, we'll call that p, and we're dividing by the distance from the field point, from the source element to the field point, and squaring. Now, in order to do this, it's actually very helpful whenever making diagrams and drawings. It's helpful not to really do a three-dimensional drawing, but to try to keep things planar. You'll see that it makes it a little bit easier. So what I'm going to do is I'm going to pick my source element ds. Remember, the direction of ds is the same as the direction of current. So it's given by this direction. Now, I'm going to choose a polar coordinate system. I have r hat, theta hat, and k hat pointing up. And given that, I'll now indicate the key quantities. This is the distance r ds to the field point, and that is the key unit vector r ds to the field point. And I'm going to indicate an angle here as phi. So what I have to do is set up this cross product, and let's just write out our pieces ids. Now here, I'm going to call, if this is the radius of the circle, capital R. Because we're using polar coordinates, I'll call that angle d theta. That's I r d theta, and it's pointing in the theta hat direction. And here's where I can just use vector decomposition. This point, dsp, the unit vector, it has a vertical component adjacent to the angle. So we have a cosine phi k hat, and we have a component. Now, you have to be very careful here because we're talking about the source element here with these unit vectors. And the component that is, it's in the minus r hat direction opposite the angle. So it's minus sine phi r hat. And now the distance, that's easier. Pythagorean theorem, that's z squared plus r squared to the 1/2. And you'll notice that this is the angle phi. And so we have cosine of phi is adjacent over hypotenuse. And sine of phi is opposite over hypotenuse. And that's all the pieces I need. I'll use those facts in a moment. So the B field at the point Z is the integral over the ring. And what I'm using here is I could call this theta prime if I wanted, d theta prime, theta prime. But I'll write it as theta prime goes from 0 to 2 pi. I'm integrating over the circle. Mu naught over 4 pi I r d theta prime theta hat cross cosine phi k hat minus sine phi r hat. Now, again, we always choose a right-handed system so that we can note it over here. R hat cross theta hat is k hat. And when we look at the unit vectors here, we have two pieces. Theta hat cross k hat, that's r hat. And theta hat cross minus r hat is k hat. Now, I'm going to separate these two pieces. I'll just write over the ring here for the moment. Mu naught over 4 pi I r d theta prime cosine phi r hat plus integral over the ring. This is what a vector integral is. You can integrate each component separately. It's theta hat cross minus r hat. That's the opposite way, so that's minus k hat. The two signs together give us plus k hat. And we have our other piece, which is mu naught over 4 pi I r d theta prime sine of phi k hat. Now, when that's telling us that the B field, notice each of these components in the cross product were positive, so the little dB that's coming from this area is at right angles to RDS and to the unit vector n this way, and so our little dB is pointing like that, and you can see it has these two plus signs. But now, when I go around the ring, and for instance, if I picked another piece over here, where the ds is directed like that, what that will do is give us a dB that's pointing in the other direction. And so what we're doing is we go around the ring, we're sweeping out a cone, and when we sweep out a cone, the only component of dB that is non-zero is in the vertical direction. And by the way, I'm claiming that this r hat integral will be 0, and sometimes it's just nice to actually do that integral. The integral of cosine phi is sine. So in order to see that explicitly, we would write r hat as cosine of theta I hat plus sine of theta j hat, and you can substitute that in there, do each of these integrals separately, and we'll leave that as an exercise for you to show that this integral goes to 0, even though we argued from symmetry that it will vanish. So this is the only piece that we have to worry about. Let's put the sign in there, and now you can see that in this integral, there's everything is a constant. The only integration variable is d theta prime, doesn't appear anywhere here. And so b of z, and let's make sure we have this right. By the way, we forgot, of course, the denominator, z squared plus r squared, which is the distance squared. So z squared plus r squared. And over here, we have z squared plus r squared. A good dimensional check showed me that I was missing that. And now I can put all of these things in, and everything comes out of the integral, 4 pi I. I'm putting in the value of sine phi. Notice I have an r squared. Downstairs, I have r squared z squared to the 3/2. This is in the integral d theta prime from 0 to 2 pi k hat. And that's just 2 pi. The 2 pi's cancel, except for a factor of 2 downstairs. And I get mu naught I r squared over 2 times r squared plus z squared to the 3/2 k hat. And that's the magnetic field of the ring. The one other point that we'd like to look at is at the center of the ring, the field, well, the z is 0, and we get this nice result, mu naught I over 2r, because z is 0, r squared to the 3/2 k hat. And one of the interesting things here is there's no factor of pi. And you might wonder why. Well, our constant in the Biot-Savart law, we had a pi, and we're integrating over a circle, which will introduce factors of pi. And so we expect that there is no irrational quantity in this answer. And that's the magnetic field at the center of a ring. That's the magnetic field along the z-axis. And unlike an electric field for a charged ring, there is a non-zero B at the center of the ring, and it's pointing upwards, and it's given by this value. And that we can use in other problems.